Good morning. Today we're going to be simplifying radicals. I gave you these papers yesterday, but you might want to start with organizing your notebook because we started a new unit number 3 on radicals. I don't have my copy of my notebook anywhere near me, so whatever your next blank page is, that's where this is going to go. And so this is our table of contents. I gave you a learning guide, so you can just glue those two in. This might be a good time to update the numbers on your notebook and your page numbers. We're going to do a little bit of perfect squares, and that'll be on a blank page, so you do not have a copy for that. And then we'll get to our simplifying radicals paper. You can pause the video. I'm going to move on. So if we are looking at perfect squares, what are they? Well, if we are to think about it, we're going to be able to make perfect squares. If we draw, there we go. I can zoom in. There we go. If we draw them, so they make perfect squares. And I like to think of this as geometry, and I like to start drawing things. So if we have, finally, my drawing tool, it works. A square, 1 unit square. It is a 1 by 1 square. What is the area? Well, 1 times 1 is 1. So 1 is a perfect square. Let's go with our list. List of perfect. Oh man, my handwriting. That says list of perfect. It does. Ooh. Squares. Should have just typed it. Too late. What's done is done. That says list of perfect squares. Go with my words. Okay. Make yours look prettier. So our list of perfect squares would be 1. 1 is a perfect square. And if we look at that, the square root of 1 gives us 1 as an answer. Now some of you are like, what? Okay, let's look at number 2 because there's a lot of 1s going on. If we look at 2 and 3, we can start to see the pattern. Okay. Now the next one, if we have 2 unit cubes, there's no combination that we can use to make a perfect square. We'll just make a bunch of rectangles. So 2 is not a perfect square. Neither is 3. We'll just make a bunch of triangle type things or long rectangles. But if we have 4 unit cubes, so I'm going to draw my 4 unit cubes here. Mostly drawn to scale. But do you see that those 4 unit cubes make a perfect square? So those 4 unit cubes make a perfect square. 4 is a perfect square because if you have 4 unit cubes, you can arrange them to make a perfect square. So 4 is the area. Ooh, that was not a good. How do I want to write this? Ooh, let's do it with like a red. 4. I'll put that 1 back on there. Red. Okay, that way you can see it. Okay, 4. And then if we look at our side lengths, that would be a 2 times 2. Okay, so if we look at the math side of this, if we do the square root of our perfect square of 4, if we have an area of 4 for our perfect square, what is the side length of that square going to be? Oh, it's going to be 2. 2. All right, next one, let's look at 3, and then we'll start to notice our pattern. Some of you have already started to see it. Good. Okay, if we draw, not move things around. Almost like a tic-tac-toe board with a box around it. Like the front face of a Rubik's Cube. Here's our next perfect square. If we have a side length of 3 times 3, our area is 9. Oh, that can fit in the tiny little box in there. 9. So 9 is the next perfect square. Because if we take the square root of 9, we get 3. Now some of you are like, what do you mean square root of 9? 9 is our area. If we think of a perfect square with an area of 9 units, how many are on one side? One side. That would be 3. 3 by 3 gives us 9. And if you think about it, it's kind of like backwards exponents. And I'm going to kind of put this to the right here, and it might help some of you over here, because that is equal to 1 squared. This is equal to 2 squared, and this is equal to 3 squared. It's kind of almost backwards of that. Kind of see that pattern here. Exponents and radicals are inverse operations of each other. So if we radical the 9 or square root the 9, we get 3. If we square the 3, we get 9. So we kind of can make that loop back around. All right, I'm going to draw one more, and then we'll just use our number pattern to do the rest. I want a 4 by 4. Maybe use a ruler. That would be a good idea. Using a ruler for this would make it look much better. Okay. So if we have a side length of 4, what would the area of this square be? 4 times 4 is 16. So if we look, 16 is the next perfect square. If we square root 16, we get a 4. We get a beautiful whole number. We don't get decimals like we saw in our calculators, because we saw a lot of decimals the other day, last class. So these are our first few perfect squares. And if we look, we can also say that 16 is the same as, let me get my green color, 4 squared. So we can use our pattern here, as we noticed, to find the next list of perfect squares here. So our next one, if we think about it, you can think about, notice this pattern of counting up 1, 2, 3, 4, and we're squaring them all. So the next perfect square would be whatever 5 squared is. 5 squared is 25. There's our next perfect square. Okay, 6 times 6, 36. That's our next perfect square. 7 times 7, 49. That's another perfect square. How do I scroll down? Oop, I just went back. Oh man, okay, the technology. I'm struggling. There we go. Next one will be 49. So 7 times 7, 8 times 8, 64. 9 times 9, 81. 10 times 10, 100. 11 times 11, 121. And 12 times 12 is 144. You should go up to the 15s, but for today, this should be enough. We'll use our math facts, and if you ever saw it on a multiplication table, it's all the numbers that go diagonal. Fun fact. Okay. So this will help us when we simplify radicals with our perfect square option, but we're going to start with option number 1 first. So option number 1. Ooh, I have a text box. Yes, okay, this helps. So the first option in simplifying, and you have 2 options, your choice. And I like to call them pairs or squares. Those are your options. You can either find your pairs or you can find your squares. It's fun to remember that way, but fancy schmancy, we're going to use our prime factorization. There, those are the words for each of those blanks. Now I know it kind of got cut off a little bit. Sorry about that. So you can glue it into your notebook and then add those extra letters as you need to. So our first option is to split it into its prime factorization, which we kind of looked at this with our exponents and simplifying. So look at 18. What 2 numbers can multiply to give us 18? 6 and 3. Oh, look, 3 is prime. It stops. 6 is composite, so we can keep going. 6 can split into 2 and 3. There we go. We split it up into its prime factorization. Now, this is I circled everything. I circled all the primes. So I always like to rewrite it out because I always write my trees separately and then I write it out. So technically, if we take this, we have our square root of 2 times 3 times 3. Now I just split it up into its factors. If we multiply that out, we're going to get 18. 2 times 3 is 6. 6 times 3 is 18. I just broke it down into its factors. Okay. So then, step number 2, and I'm going to change my color. That way you can see it. If you want a color code, go for it. Okay. So we're going to circle the pairs. Do we see any pairs that are the same number? Yes, we do. We have 3s. So we circle the pairs. That's a pair. We can factor out that pair to the front. To the front. We can get it outside of the radical. Get it out of there. If you have 2 pairs that can be factored out, you can then multiply them together. So if we had like a pair of 3s and a pair of 4s, we can multiply them out. So that will come in handy later, but we don't actually have that yet. But if you were wondering, we multiply them. We'll multiply, there we go, I almost missed the L there, them together. But we don't have that. In this example, we just have a pair of 3s. So when we factor it out to the outside, that 3 times 3 would be our 9, which is a perfect square. Now, we don't have to multiply to get to 9 because we're just going to go right back to where we were. But those pairs turn into 1, 3, because that pair of 3s, if we're looking at it, would just be that one side length. Now, my explanation sounds really funky right now. So sorry. And then we put whatever's left, and we leave it in the radical. Now, the pairs is easy to find, and we have a pair of 3s, so we put that 3 on the outside. It'll make a bit more sense when we do our perfect square method. I hope that'll clear some things up. If not, we'll talk about it in class. So bring all your questions to class. We multiply together the non-pairs as well. So if there was something left with that 2, like a 2 and times 7 in there, then we multiply those. So anything that we have a few of, we'll multiply together. So 3 root 2 is the simplified version of the square root of 18. Now, let's look at some examples and go through. So if we have the square root of 72 and we're using our prime factorization method, we'd start with our tree and we'd split that up. So 72 can split into 8 and 9. Both are composite. So 8 we can keep splitting up into 2 and 4. Ooh, 2 is prime. That one stops. 4 can split up into 2 times 2. 9 can split into 3 times 3, but those are both prime. Okay, so we have them all. The tree is done. Some of you are going to like this method just because of those factor trees. Now that we have that done, we're going to rewrite it. It always helps to kind of rewrite it visually. And when we put the prime factorization, we always want to put it in numeric order, like least to greatest. So we'd put 2, 2, 2, 3, 3. So we'd have our 2 times 2 times 2 times 3 times 3. Oop, and I got to extend my radical bar, make it a little bit prettier than that. Oh gosh, no, that's not so bad. If we multiplied that out, we would get 72. So we just broke it down into its factors, just like we did with our exponents. From here, we find our pairs. Only pairs. So if we look for our pairs and we circle them, we have a pair of 2s here, and we have a pair of 3s here. There's a 2 that's left out. That's okay. So our pair of 2s gets brought to the outside. So we have a 2 out here. And that 3 also is brought to the outside here. And what do I mean by outside? Outside of the radical. They've been factored out. We used our prime factorization to factor out those pairs in there. And then this 2 that was left over just gets brought down and left in the radical. Now, we talked about if we have things on the outside. If you have 2 pairs that can be factored out front, multiply them together. Okay, so 2 times 3 is 6. And then we have our root 2. We can do this with variables as well. Okay, so let's do our tree for 32. So 32 can split up into 8 and 4. 4 can split up into 2 and 2. Those are both prime. 8 can split up into 2 and 4. 2 is prime. 4 can split up into 2 times 2. That's a lot of 2s. 1, 2, 3, 4, 5. 5 2s. Okay, so we're going to rewrite this with 5 2s. 1, 2, 2 2s, 3 2s, 4 2s, 5 2s. Okay, I got 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So then, technically, x squared, we could split up into x times x, which we also know that x squared is x times x. Okay, so we have times x times x. And then technically, our y cubed technically can be split into y squared times y, and then we could split our y's if we're going for factor trees, but most of us are pretty good. We know that that can just be 3 y's right now. 1, 2, 3. I almost didn't make it. Okay, It's a lot of numbers, but it helps with the pairs. A lot of students like the pairs because they can see, oh, there's 2, there's 2, there's 2. And it's easier than finding perfect squares if that last page was a little funky for you. Okay, so let's find our pairs here. Ooh, look, we have a pair of 2s. We have another pair of 2s. Okay, no more pairs of 2s. That one has no other buddy. It stays. Okay, what about, our x's? We have a pair of x's. And our y's, we have a pair of y's. All right, so this pair of 2s goes to the outside to become 1, 2. We've just factored it. Those 2s go together to be a 2. That x goes to the outside. And that, well, just the y goes to the outside. And then we have our radical with whatever's left over. Well, that 2 and this y were left over, so we have a 2 times a y. Okay, now let's write that prettier, because we don't really write those dots anymore. We just put the variables next to each other, and we put the coefficient out front. Oh, and hey, look, 2 times 2, we can multiply that, which would be 4xy. And then we have our square root of 2y. Lovely. We'll definitely, maybe we'll do a few practice problems in class, a little extra notes. It's an early morning. Okay, here we go, number 1. Option number 2. Now, if you like the perfect squares, this method does go faster. My mental math students who really enjoy mental math, this will be the method you prefer. But those of you who are visual with liking to see it all, this prime factorization with all the pairs works really nicely. So it's just kind of preference, which method you want. Okay, so the first thing you're going to do is find a perfect, I don't want to capitalize that because it's in the middle of the sentence, perfect square. I kind of lined it up for the blanks. You're going to find a perfect square that is a factor of the radicand. Radicand is one of our vocab words, meaning the number within the radical. Radicand. Sounds like eradicate. Okay, but we're not talking about Pokemon. Here we go. So it's a factor of 18. So something that it can split up into. So not quite doing the whole trees. We're just finding a perfect square factor. And we split it up into 2 radicals. Oh, I'll type that one. 2 radicals. So we're going to split it into 2 radicals. What am I talking about? Okay, here we go. I'm going to move my face over here. Okay. So when we do this, we're going to find what is a factor of 18. What can 18 divide by evenly? That is a perfect square. You can always go back to the notes and start going, okay, 18, well, 16 can't divide into it. And you go back 9. 9 works. 9 is that perfect square we're going to use. 1 can work, but 1 just kind of brings us back to 1. 1 doesn't really help us, so we're not going to use 1. 9. Okay, where is the, there we go. So if we split this one up into 9, we're going to split it up, there we go, into that factor of 9. And I always write the perfect square first, just because it's closer to the outside, because we're going to factor it out, times, okay, 9 times what gives us 18? Oh, 9 times 2. Now we're going to split it up into 2 radicals, because we know this from our calculator day with Desmos. If we have the square root of 9 times the square root of 2, that can simplify back to the square root of 18. We're just going backwards, factoring it out, splitting it up. Now, why is this important? Okay, here we go. So the square root of 9, we know what the square root of 9 is. Look back at your notes. If we have a perfect square with 9 units as our area, oh, my face is in the way again. It's like asking what, nope, I didn't want to draw. It's like asking what is the area of that square that's over here that obviously I can't get to. There we go. So if we have an area of 9, what is that side length? The side length is 3. So the square root of 9 is 3. Wonderful. So square root of 9 is 3 times our square root of 2. Oh, look, we simplified it. The toughest part is figuring out what is a perfect square within 18, or what do we do if we have 2 perfect squares? That one gets a little complicated. But this method does go a bit quicker. It's a little trickier. So we solve the perfect square radical and write the number out front. We wrote it out front. Right? We found that perfect square, 9 the square root of 9, because 9 is a perfect square. We square rooted it, found that side length of the square, which is 3, which is out front of the other radical that cannot be simplified. 2, we can't make a perfect square with 2 unit cubes. It stays in the radical. Done. If you do not choose the highest perfect square factor the first time, you do it again. You break down the radical again. So sometimes you'll do this twice, unless you can find that greatest perfect square, the highest perfect square, like a greatest common factor, but the greatest perfect square factor. You break down the radical, and then once it's on the outside, just like we did with the numbers on the outside in the last one, we multiply the numbers in front of the radical together. So let's do that here. Oh, look, 180. That factor, doesn't that also have a factor of 9, just like this one? Yes, it does. So we can factor that one out to be, well, I don't want to do that because then it looks like the trees. 9 times 20. Because 9 is a perfect square. And 9 times 20 is 180. Okay, then we can split up into 2 radicals. Square root of 9 times the square root of 20. Okay, and then which one of these can be simplified? Well, not the square root of 20. That one stays. 9! Square root of 9. If we have an area of 9 for a square, what is the root of it? What is that side length? Oh, 3. Okay. Now, if you think you're done, this might not be the method for you because there's still a perfect square factor within 20. So be careful. That's why a lot of students kind of drift to this method, because you know once you pull out all your pairs, you're done. And if you miss a perfect square factor in this 20, so that's why a lot of students like the pairs. The pairs are nice. So 20 has a perfect square in it. What would that perfect square be? 4. 4 can make a perfect square. Okay, so let's do it again, as we talked about. So we can split this up. No, I don't want to do that so it doesn't look like the trees. Okay, so we have 3 times the square root of 4 times 5. Okay, so we have 3 times the square root of 4 times the square root of 5. So this would be 3 times, if we have a perfect square of 4 areas, we divide that to get our side length. Our side length is 2. 2 times 2 gives us 4 as an answer. Oh, lovely. Times the square root of 5. And then we just multiply our coefficients. 3 times 2 is 6 root 5. 5 is prime. There's definitely no other perfect square in there, and we can't make a perfect square with 5. So it works very nicely. You could also, if you saw that 36 was a factor of 180, you could have done that in one step because that would be the highest perfect square. So, but you got to know those factors. Let's do another one with 200. 200 there. Okay, let's think about 200. What would be the perfect square of 200? Well, we're going to go towards the larger numbers here. Well, if we look, 144, nope. 121, nope. 100, oh yeah. So that would be the perfect square we're going to factor out of there is the 100. Awesome. Okay, so we're going to split up that one into 102. I'm going to start a little bit over here because I think I'm going to need some space. So we have 100 times 2. We split up that. Now with our variables, we want to split it up into squareds. 2s, pairs of 2. So it's like kind of like pairs. And sometimes, honestly, I like to mix the methods. So I personally use the perfect squares for my coefficients, and I use the pairs for my variables. Because I can. But for our perfect squares, we want to split it up into anything with a perfect square. So A, there's just one A. We can't break it down into A times A because it's just A. So that one just stays. That one's going to stay in the radical. B squared. Oh, done. It's a perfect square because it's squared. So we have B squared. C cubed. Technically, if we wrote that out, that would be C times C times C. We could regroup that to be C squared times C, which is what we're going to do. That way we have a squared in there. So we'll put times C squared times C. And then same thing with D to the 4th. We know that's D times D times D times D. But if we want it into squareds, we can pair up these two to make it D squared times these two, which would make it D squared. So we'd have times d squared times d squared. All right, now, from here, what we normally do is we simplify all of our perfect squares. So I'm going to go through, and this one is a perfect square, so I'm going to rewrite it. I'm going to rewrite it a little extra. Usually I don't always do this, but I'm going to rewrite all my perfect squares together. So I have 100. I have my b squared here. I have my c squared here. And then I have two separate d squareds. Okay. And then we're going to take all the things that could not and do that in our second radical. And of course, as I talked about with mental math, this step might be the one you skip if you're using mental math for some of this. But these are our notes. So we'll write it for today. All right, every term is accounted for, or I guess every part is accounted for. All right, so this is going to stay in the radical, that square root of 2ac, because there's nothing else to be factored out. All right, the square root of 100. Well, if we have an area of 100, that side length is 10. B squared, what is the root of that? Just b, because if you notice, the square root of a square cancels it out. They're inverse operations of each other. They just cancel each other out. Same thing, c squared turns into a c, d squared turns into a d, and d squared turns into a d. Now, we can simplify that because d times d gives us d squared. If you can start to see the pattern, you can do some of those variables a bit quicker, all the way from the d to the fourth power, and just split that up into d squared when you factor it out. That works. Times the square root of 2ac. Make sure to bring all your questions next class. I feel like we'll do a little bit more notes because this is some funky stuff. Awesome.